Today we're going to be working on finding intercepts of functions, and we will want to be finding the x-intercept or intercepts as well as the y-intercept. And we'll work through three levels of equations: basic, intermediate, and advanced. To find x-intercepts, set the equation equal to 0 and find the solution or solutions. So this means that there may be more than one answer for x-intercepts. To find the y-intercept, set x equal to 0 and simplify. This means there is at most one y-intercept. And finally, I would like you to express your intercepts as coordinate pairs. So in the most basic function, here we go, y equals 2x minus 5. To find the x-intercepts, we are going to set the equation equal to 0 and add 5 to both sides, divide both sides by 2, and we express the x-intercept as a coordinate pair, x comma y. Finding a y-intercept, we are going to set the equation equal to, not equal to 0, we're going to set the x value equal to 0, and then we'll simplify the expression. So we plug 0 in for x, simplify, and we get a y-intercept of 0 comma negative 5. So typically there is going to be one or more x-intercept and only one y-intercept, but we will see examples where these may not even exist. So let's look at example number 2. Example 2, or 1b I should say. We have a rational expression here. We want to find the x-intercepts. X-intercepts come by setting the equation equal to 0. I multiplied the denominator across, then I added x to both sides, and that gave me an x-intercept of 7. So I express it as a coordinate pair, 7 comma 0. Moving to the y-intercept, I evaluate f of 0, so I plug 0 in for all of the x's. I simplify the value, and that gives me a y-intercept of 0 comma 7/3. Okay. Moving on to example 1c. So sometimes you have an expression that is a little more complicated looking. It might benefit you to do some simplifying or factoring and create an easier looking expression to work with before you start finding the intercepts. This usually is the factoring step, but this is not a factorable expression. To find the x-intercept, we set the equation equal to 0, add 1 to both sides, divide both sides by 2, and we get 1/2 comma 0. To find the y-intercept, we set x equal to 0 and we evaluate the expression. So g of 0 in this case is negative 1. So we have a y-intercept of 0 comma negative 1. Remember to always write your intercepts as coordinate pairs. Moving on to example 1c, we have, oops, we just did 1c. 1d. We have a expression. It is another rational expression, and we should see if anything is factorable, and both the numerator and the denominator are non-factorable. So we'll jump into finding the x-intercept, which consists of setting the equation equal to 0. Now, as I multiply the denominator across, I have 0 equals the numerator, subtract 1 from both sides, and I get the statement negative 1 equals x squared. If I were to square root both sides, I would get an imaginary answer. Thus, there are no x-intercepts. So this is a curve that has no x-intercepts. Going for the y-intercepts, I plug 0 into the x's. I simplify the expression. I get 1 divided by negative 7. And there's my y-intercept of 0 comma negative 1/7. Okay. Finally, let's look at example 1e. And in 1e, again, finding the x-intercept, we set the equation equal to 0, multiply the x minus 1 across, and we get 0 equals 5, which is not a true statement. 0 does not equal 5. That's false. So because we arrived at a false conclusion, this is another case where we'd say there's no x-intercepts. And then when we want to find the y-intercepts, we set x equal to 0. Simplify the expression, and we have a case of 0 comma negative 5 being the y-intercept. So those are considered basic intercepts. To move on to the more intermediate intercepts, those are the ones that are going to have you flex on your factoring skills. So example 2a, we get a quadratic, and this quadratic we can apply the AC method to, and it factors to x plus 2 plus x plus 3. You can factor by whatever method you wish, but the end result is x plus 2 times x plus 3. When we set that equal to 0, we are going to apply the zero product property, which means either the first term is 0 or the second term is 0. Solving each of those term equations, we get two roots or two zeros for the function. And this allows us to see that there are two intercepts. One of them is at -2, 0, and the other one is at -3, 0. I put those 2 points in curly braces to signify that this is a set of intercepts. So some people might write "and" between those two, but the curly braces is using the set notation. Finding y-intercepts is a matter of plugging in 0 for x, and we simplify that expression, and there is only one y-intercept. There will never be more than one y-intercept. Okay. Moving on to example 2b. 2b is a rational expression. If we factor the numerator and the denominator, this will give us a leg up on solving the equations that we need to do for finding intercepts. So I factor the numerator using the AC method. Then when I solve this equation, I'm going to set the equation equal to 0, multiply the denominator across. This applies the zero product property, which means either the first term is 0 or the second term is 0, which gives me two solutions, 7 and 1. Therefore, there are two x-intercepts, one of them at 1, 0 and the other one at 7, 0. Again, I put them in curly braces to signify the set of the 2 points. Finding the y-intercept is a matter of plugging in 0 for x, so I stick 0 in for all of the x's. I simplify the numerator and denominator, and that gives me a y-intercept of 0, 7/3. Okay. Moving on to example 2c. This is a quadratic that requires a little more effort in the AC method. We split the middle term and we factor by group, and we arrive at a factored form. The factored form of polynomials is always the best form for finding intercepts, in my humble opinion. So to find an intercept, we are going to set the equation equal to 0, and we can apply the zero product property. The zero product property yields two different intercepts, and we can express those as point and a point inside the curly braces as a set. The y-intercept is a matter of setting the x value to 0. So we evaluate the function at 0, and we get a y-intercept at 0, -9. Continuing on with example 2d, I have a rational expression here. After factoring the greatest common factor out of the numerator, I saw a difference of squares, so the numerator has been fully factored. When I solve this by setting it equal to 0, the 4x plus 3 multiplies across, and we have 0 equals the numerator. This gives us 3 terms in the zero product property. The first term equals 0, the second term equals 0, or the third term equals 0. And that gives us 3 solutions. So 3/5, 0, -3/5, 0, and 0, 0. This is the set of the 3 x-intercepts, so I put them inside the curly braces. Finding the y-intercept is a matter of evaluating the function at 0. Plug 0 in for all of the x's, and we get 0 divided by 3, which is 0 over 0. Or sorry, which is 0 divided by 3, which is 0. So we have a y-intercept of 0, 0. This should be something that you note. If you ever have an intercept that is 0, 0, it will appear in both the x-intercept and the y-intercept. And the last intermediate example, we have a factorable expression. This is a rational expression. When I factor the numerator and the denominator, I arrive with difference of squares on top and the AC method on the bottom. And when I set this equation equal to 0, I should note that that term x minus 3 cancels out of top and bottom. This means when I multiply the 2x plus 1 across, I only get 0 equals x plus 3, which produces one x-intercept. If I did not note that this term canceled, what would happen is I would say that there is also an x-intercept at 3, 0. Unfortunately, the function is not defined at 3 because that creates a divide by 0 error. What is going on graphically is there's actually a hole located at x equals 3. And that's kind of a concept beyond intercepts, but please note that if terms cancel, you should cancel them before finding intercepts, because that's usually the indication that there is a hole or an asymptote of some sort. Okay, moving on to the y-intercepts, we plug 0 in for all of the x's, we simplify the expression, and that comes down to a y-intercept of 0, 3. Okay, that concludes the intermediate function intercepts. The advanced intercepts relies on generally more challenging factoring problems or higher level algebra skills. So in this first example of advanced intercepts, I had a third degree polynomial. I used factor by grouping and difference of squares, and that gave me 3 x-intercepts by applying the zero product property. Okay. This is something that you would probably see on a intercepts test in my class as kind of the higher level problem, because it is a more challenging factoring. Finding the y-intercept though is pretty easy. We plug 0 in and we get our y-intercept. Y-intercepts are always very easy to do. They're just evaluating functions. The next x-intercept, this probably would show up in my unit on exponentials, but not on the Big Ideas Intercepts test. This is a exponential expression. Finding the intercept requires an understanding of how to use logarithms to solve exponential equations. And I put this here mostly for people to start getting a preview of logarithms. If you already are familiar with this, then great. But add 5 to both sides, take the log of both sides because that drops the exponent down, divide log of 2 to the left, and then add 1 to both sides. As I said, evaluating y-intercepts is easy to do. Plug 0 in for x and simplify the expression. We get 1/2 minus 5, which is negative 4.5. Okay, our next x-intercept is from a logarithm. The logarithm, we're going to subtract 2 from both sides, then we'll exponentiate both sides. We get 10 to the negative 2 equals x minus 5. And add 5 to both sides, and we have that as an x-intercept. Finding the y-intercept, we plug 0 in for x, and when we see that we're taking the log of a negative number, we know that logarithms are undefined on negative numbers. So there is no y-intercept for this curve. In order for there to be a y-intercept, the logarithm would need to be a positive number, but it is not. Okay. Example 3D, we have another logarithm here. And so with this logarithm, because it is a natural logarithm, we can use the number e to solve the expression. So subtract 1 from both sides, exponentiate both sides. E to the negative 1 equals e to the ln. The e and ln cancel, and we get an expression. Again, this is a preview of things to come. This is not really part of the intercepts test, but it is worth writing down if you're trying to develop your math knowledge. Finding the y-intercept, we plug 0 in, and again we get a logarithm of a negative number which is undefined, so this curve has no y-intercept. Finally, on the last one, we have a trig function. we will do units on trigonometry. So this is advanced in the sense that we haven't learned trig yet. 0 equals the function. We do the same process. 1/2 equals sine x. We added 1 and divided by 2. And then if you've learned trigonometry, you know that sine of x is equal to 1/2 at these two angles on the unit circle. And then if we want to account for all of them, we have to add multiple rotations. So we have pi 6 plus 2 pi n. Again, this last one is diving deep into the world of finding intercepts, and if you haven't learned trig, I would not stress on understanding this one deeply yet. But finding y-intercepts is very easy. We plug 0 in for the x value. Sine of 0, we can grab a calculator and evaluate, or use our unit circle, and we get an answer of -1. So this curve has a y-intercept of -1. Okay, that concludes our video on function intercepts. Please note that these more advanced ones, particularly the last 4, is deeper than you would see on an intercepts test. So an intercepts test is going to be quadratics and rational expressions, as well as the linear ones. So thank you for watching. Be sure to comment, like, subscribe, hit that bell for notifications, and have a great day.